So I would start the quadrature phase shift keying, which is our next topic. Let's concentrate on this one. Uh, as I mentioned earlier, that we studied the one-dimensional signaling scheme, the binary phase shift keying, which was actually a one-dimensional signaling scheme. So the discussion in this section considers a two-dimensional signaling scheme. So we would concentrate on two-dimensional signaling scheme, quadrature phase shift keying, as the name says, quadrature. So they are in phase quadrature. The two signals which we will come to know in a short while. Basically, it's a two-dimensional signaling scheme. If you observe your signals in the Euclidean space, the signals of the QPSK, it will be in two-dimensional, or you need two basis functions to represent a QPSK signal. So QPSK is two-dimensional signaling scheme. The expression for QPSK can be obtained from equation 3.21 for m equals 4. So actually m equals 4. If you observe equation 3.21, it is very similar. It is very similar to this equation, right? It's actually the same as this equation, but here you have I, which is from 1 to m, and we have fixed m over here, which is 4 now. In our case, our m is 4, so we have fixed the value of m. So we are choosing m equals 4. So for QPSK signaling, we have m4. M4 represents that we have 4 unique symbols or signals, 4 unique signals or 4 unique symbols. And you can see from this expression, when as it is mentioned that I varies from 1 to 4. So if you substitute I equals 1 here, it will be a cos of 2 pi fct plus theta 1. So similarly for I2, it will be S2 of t, your second signal, which differs from the first one by theta 2, this angle, theta 2. Similarly, S3, you have theta 3. And for S4, you have a cos of 2 pi fct plus theta 4. All the four angles, all the four signals, they differ from by this their angles only. This is the only difference. And this is the phase difference between these different signals, or we say m unique symbols. So in QPSK we have 4 unique symbols or 4 unique signals for transmission. Now if you see the next line, here we have used the identity, mathematical identity, which I discussed in my previous video, that cos of alpha plus beta, which is cos of alpha plus cos of alpha cos beta minus sin alpha sin beta. So if you substitute this expression, you will get the next line, this one, cos alpha cos beta cos theta I cos 2 pi fct minus sin alpha sin beta, and a is over here. Well, you can represent this one, this equation, as a linear combination of psi 1 and psi 2. Very important, linear combination. You can see that we represent our QPSK signal, each QPSK signal, as a scaled version of psi 1 and psi 2. So as I of t, the ith signal is can be represented as the sum of the scaled version of these basis functions, and you already know the basis functions, right? So if we go to the if we observe our basis functions, so you can see the basis functions, the basis functions which are used here, psi 1 of t and psi 2 of t. If you go back to my previous slides, there I mentioned actually that your psi1 of t, your psi1 of t is under root 2t cos of 2 pi fct. So this is a sinusoid. Similarly, your psi2 of t, if you go back to my previous videos, you will see that we learned about psi2 of t as equal to negative. We put negative sign over here, sine of 2 pi fct, and I told you that we will come to know about the importance of this negative sign later on. So actually in QPSK it will be very clear that what is the importance of this negative sign. So if you observe over here, see this negative sign, if it is like absorbed in the psi2 of t, you can represent this difference as a summation. So you can see that it is actually the sum of psi1 and psi2. This symbol is actually the sum of psi1. So this is what we get by putting that negative sign there. Just we want to see this ayat symbol as a linear combination, of psi1 and psi2, which is shown here in this equation 3.22. Now here psi1 and psi2, as I mentioned earlier, these are the orthonormal basis functions which we discussed in details in previous lecture. It is given in these equation 3.14, and the si1, s sub i1 and s sub i2 are what they represent. They actually represent the image of the ayat signal si of t over the basis function psi1 of t and psi2 of t respectively. And as we see that we can obtain this image, if you recall your previous knowledge, that the image of the any signal over psi1 can be found by integrating this by finding this dot product, by finding out this dot product. So si of t, if you observe si of t, s sub i1, which is the scalar, and it represents the image of the ith signal over psi1, it can be obtained by solving this integral. So if you substitute si of t from here, from this equation 3.22, which is given here, and you just multiply it with psi1, you would get this equation. It is very easy to prove actually. I hope that there is no difficulty, but let me do it for you. So if I solve this equation, actually the equation says, and you will have si1 psi1 square of t dt plus the second integral, which would actually the second integral, which would give you we have a second integral over here, and that second integral would give you 0, because psi1 and psi2, if you multiply, they are orthogonal. You integrate, you will get a 0. So I will not solve this integral. This will give you 0, right? Here you will get a 0 as a result. So you will get a 0 here. So I'm not going to solve this one. If I solve, let me solve it. Okay. So if you solve this one, now it's easy to see that it is actually psi1 square is the energy of the signal, and si1 you have already you are already familiar with this si1. So you have what do you have? You have the, if you closely observe it, you have the actually you can say this is Si1. So we can just Si1 is a scalar, so we can just put it outside the integral. We can write it outside the integral. Inside is psi1 square of t dt. Now this square integral, the square and integral of this signal, this is of course the energy of the signal, right? So this is the energy of the signal, and we already mentioned that this one is unity, orthonormal basis function. So here we are left with Si1, and if you observe your Si1, that is actually plus E cos of theta I, plus E cos of theta I, as I mentioned earlier. This is plus E cos of theta I. So you can always prove this identity 3.23, that your image Si1 is the image of the signal over theta. Now this similarly Si2 can be verified that it is under root E sine theta. Well, this square root E cos theta will be seen in a short while while we discuss the Euclidean space. Theta is the angle, and you can find out theta by just taking tangent inverse of the s sub I 2 over s sub I 1. Now what as the signals differ, these QPSK signals differ by their angles only, and you can find out the angles which is shown in this table as well. These angles are given by pi by 4, 3 pi by 4, minus 3 pi by 4, and minus pi by 4. You can see these angles in table 3.1. Now if you closely observe this table, it says that as I mentioned earlier, that these four signals differ by the angle theta I. So phase theta I is pi by 4, 3 pi by 4. These are the four different phases, which is actually 45 degrees. Then you have 135 degrees, and so on. 3 pi minus 3 pi by 4. You can check these in degrees. So now if you concentrate on the first line, the top row, here divots are represented. Here the phase of these different angles, the ith angle is represented, and these are in the next two columns we have the first the x coordinate, or the coordinates along psi1, and the coordinate along psi2, which is under root E cos of theta and under root E sine of theta. Now how do you write this one, right? Let's see here. Well, if you observe your signals, from here theta in your generalized expression which I gave you for MPSK, you can find these theta. You will get pi by 4, 3 pi by 4, minus 3 pi by 4, minus pi by 4. But see what actually the concept which is given over here is important. The concept which is given is important, because if you see your data, usually your data would be in the form of ones and zeros, right? So it's always in the form of, like, suppose this is your data 1 1 0 0 1 0 1 0 0 and something like this. If this is your data, usually your data is in the form of bits. Now with QPSK signaling scheme, where we have four unique symbols, each symbol can carry 2 bits, so we can just divide this data in the group of 2 bits, right? And when you divide the whole sequence, all the bits in the group of 2 bits or divide, you can have these four unique divides. You can have 1 1, you can have 0 1 0 0, or 1 0. No other possibility, right? Because it's just 2 bits. So 1 0 1 1 0 0 1 0. All these are possibilities, and so these will repeat. These four bits will repeat again and again. Like these, one of these 4 die bits will repeat again and again in the whole sequence. Now if you are having this sequence, now you can see that 1 0 is represented by a signal. This can be mapped to a signal for which we have theta minus pi by 4. Similarly, 1 1, for 1 1 we have theta I pi by 4. So whenever we want to transmit these signals, we would choose a particular, a unique symbol, a unique signal. We would choose a unique, for example, we need to transmit 1 0, so we would choose our theta I to be minus pi by 4. The next 2 bits are 1 1, so we would choose our theta I, it will be pi by 4. The next 2 bits are 0 0, so the next symbol that would be transmitted is with the theta minus 3 pi by 4. The next is 1 0, so the next bit which will be the next signal or symbol which will be transmitted is with this angle. Now when you have these angles, as I mentioned, that these angles, it's very important to know that with these angles you can see how do you get these coordinates. It's very important to know how do you get these SI1 and SI2 like this. So if you observe your signal, if you observe your signal over here, it is it can be your QPSK signal is actually a 2-dimensional signaling scheme. Let me show you how our signals, we can get these, we can view it, QPSK signals in the Euclidean space. So we have psi1 of t here, we have psi2 of t here, and as the first symbol, which for a diabit 1 and 1, for a diabit 1 and 1, you can see. So now before going to this one, let's suppose our data is in this form: 1 0 1 1, right? 1 1 0. Let me erase it. Let me erase it. So suppose our data is in this form: 1 1 0 1 0 0 1 0, and so on. This is our data. So using a QPSK modulation scheme, whenever you encounter, you can group your data in die bits, group of 2 bits, right? Or group your data in group of 2 bits. Now you can transmit these bits by using 4 unique symbols or 4 unique signals which we have actually in our in this QPSK modulation scheme. So for 1 1, we can see that our SI1, our signal SI of t is the linear combination of psi1 of S1t plus psi2 of t. So it's a linear combination of psi1 and psi2. And for the first, if you observe it closely, SI1 and SI2 can be plotted here, which means that with this position vector, which is at an angle theta I of pi by 4, represent this position vector represent the first symbol S1, and the coordinates here are given. The coordinates are given in your notes. If you observe your notes, the coordinates are given, which is under root e over 2 and under root e over 2. So these are the coordinates of this point, right? These are actually the coordinates of this point. Similarly, you can draw all these 4 points in Euclidean space, and you will get a point over here. You can draw all these 4 points in Euclidean space. These are the 4 signal points for QPSK. The position vectors can be drawn, right? And you can see these angles theta 1, theta 2, theta 3 and theta 4. You can write all these coordinates. So whenever you encounter in the sequence 1 1 the modulator or the transmitter would transmit signal S1. Whenever it encounter 0 1 it would transmit S2. Whenever it encounters, this is for 0 1, right, this bit sequence. Similarly, whenever it encounters 0 0, it would transmit this one, S3, and S4 with both coordinates negative. So this is for 1 1, then 0 0 bits. This we transmit this signal for 0 0, and here it is 1 0. S4 is transmitted. So the data would be transmitted using these signals. So here it's quite clear. You have for QPSK, the theta i's are given here in this table 3.1. And now it should be noted that each symbol, it should be noted, very important point here, it should be noted that each symbol Si of t can carry 2 bits of binary data, and the data rate increases by n times as compared to BPSK. So the data rate increases by n times as compared to BPSK. N is log 2 of m. So log 2 of m is, you can see. So if you want to find out the relationship of n and m is given, n is log 2 of m, your m is 4, so log 2 of 2 raised to the power 2, and which is equal to 2 times log 2 of 2, and this is equal to 2 because this is unity. So the data rate increases by n times. Here this is very important relation, n log 2 of m. When you have m unique symbols, each symbol can carry n number of bits. M unique symbols, each symbol can carry n number of bits. So this is all about the QPSK, just an introduction to QPSK signaling scheme. Our next topic will be the QPSK signal constellation.